Hello YouTube viewers, welcome to my show Future Friday. In today's episode we're gonna discuss about other moons of the solar system. So let's dive right into it. Now, continuing our moon series, we have to first lay down some ground rules. Now, rule number one is basically anything that is bigger than 300 kilometer would generally, more often than not, would be a spheroid. Basically, it would be a sphere, either would be stretched or squashed or something like that, but it will be sphere, more likely or not. That's because of gravity. Now, what happens to anything smaller than that? Basically, let's say you find something that is 200 kilometer and it will be like more or less sphere, but you can easily tell it's not a sphere. So you have to understand that. And it will be affected by the composition of whatever you are talking about. Let's say 200 kilometer of iron would be completely different than, let's say, 500 kilometer of ice. So, but as of now, our current understanding, current calculations suggest that anything that is 300 kilometer or larger in terms of diameter would generally be more or less sphere. Now, it must have a planet to orbit, otherwise what's the point of calling it a moon? We will call it either a protoplanet, same way we call Pluto a protoplanet, or we'll call it something else. Now, it must be stable in short term. Now, when I classify stable in short term, you must understand short term in terms of planet life, not in terms of human, because short term for human is like basically few days or few years. Short term for a moon is generally classified in few million years, because you have to understand moon that we have from Earth is basically was very close to Earth. Then it slowly started to drift away. Somebody says like it's drifting upwards of 1 inch per year. Now, all things aside, it will over time will fade away. So, but again, would planet be still here? Yes. Would sun be still here? Yes. Because from context of a timeline of a planet, it's still short term. Now again, there are different moon with different orbits. Some orbits are much longer stable. Some orbits are like so stable that they will literally outlast sun. But more or less, it must be stable in short term. Basically, at least few million years. Then we talk about like obvious, it must be natural. Otherwise, we will start calling our own satellites moon. So there are many moons, like we have Europa, we have Triton, we have Titan, we have Ganymede, we have Moon, we have Callisto, we have Io. So first and foremost, let's talk about Mars. Now Mars also has moon, it has two moons, but you have to understand our moon is 600 kilometers in diameters. These puppies are barely 22 kilometers and 12 kilometers, so they are very small. They are more or less like a capture asteroid. Now if this is the size of Mars, true scale, then the tiny dot here that you may not even be able to see is basically Phobos, and there is the very tiny dot at the end that is Deimos. And this, if you cannot find those dots, that's the whole point. It is that small. Literally, it is that small. Now, you have to understand these orbits are not similar to our own orbit. It does not take 30 days or 50 days. The orbits of basically Phobos, the smaller one, is very fast. It orbits around like this. It's almost like low Earth orbit, quote unquote. It's 7.6 hours. So literally you can see it rising and falling 2 to 3 times a day. And then you come out Deimos, even though it's far, it's not that far, and the orbit speed is still high, so it will orbit in around 30 hours. So you can see it like every other day or something like that. So what are the purpose of this? These are not big enough to do anything useful, and they are not small enough to ignore, but they do serve as a very good radio outpost. One of the most frustrating part about watching the movie Martian is that somehow, like, we had the technology to make tiny rovers which has radio communication to Earth, but we built giant habitats and it did not have redundant communication system with giant rovers. That was frustrating. But like, again, we can utilize these because you have to understand, we cannot put any orbits, any satellite or anything like that in an orbit that will interfere with this, because it will intersect and sometime it will collide. So why not use this directly? This is, while it is quote unquote small, is still bigger than any satellite we can put. So using the large surface area allows you to put very large radio dishes and will allow you to put a lot of solar panel, which will allow you to have much higher signal to strength ratio, and you have them. Utilizing them would be a wise choice. And this concept was shown in the TV series Expanse, and there they had a war going around, and one of them was a very good listening post. So it does make sense, because from a radio standing point of view, bigger is better. You cannot go bigger, basically bigger than 12 kilometers or 22 kilometers. So using them, they had like hundreds of dishes, radio dishes that were, and you can build really big radio dishes because there is no gravity. Or as long as you can deposit metal there, heck, you can convert this whole thing into a basically radio dish. So it is really useful for radio communication, and it can also act as a very small outpost. Now we come to the interesting part. We come to Titan. Now Titan is very interesting simply because it is the biggest moon of Saturn. Saturn and Jupiter are the two daddies of the basically our solar system, and both of them have long list of moons. They don't have one moon or two moons, they have list of moons. So when we are talking about Saturn, you must not take this lightly that it has like a largest moon of Saturn. To give you a context of its size, Earth, Moon, Titan, basically it's bigger than moon and it's much more massive than moon. Now the interesting part about it is, okay, it's a moon, it's a big moon. What's the interesting part about that? It is the only moon known to us in terms of our solar system that has atmosphere. Not only that, the atmosphere is actually thicker than Earth's atmosphere. Basically you take a barometer and calibrate it to Earth's sea level, you will get 1 atmosphere. You put that here, it will go to 1.5 upwards of atmosphere. It is actually denser here than it is on Earth, so that is very unique. You can travel there. Now you might be like, wouldn't we need pressure suit to survive that? No, that 1.5 atmosphere, that's why we can do deep sea diving. Our body can accept it as long as you have good oxygen supply. You can handle that kind of pressure. It will be frustrating at first, but you can handle it very easily. Now this place is the coldest on solar system. Now when I mean coldest, I don't mean in terms of lowest temperature, because that has been recorded during the deep parts of the crater of the moon. That is like almost absolute zero, but this is still the coldest. What the hell? Because it only goes to 93 Kelvin, aka minus 179.5 degrees Celsius. Basically it's not even cold enough for liquid nitrogen to form. That's why the atmosphere is nitrogen. But then again, why I'm calling it the coldest place? Think of it this way: if you are classifying space, vacuum of space, all you are truly saying, there is no radiation source nearby, or there is nothing that traps radiation, because you cannot give a temperature to vacuum. There is nothing to have that temperature. So when you put, let's say, a solid block of aluminum that is heated to, let's say, melting point, and you put it in moon, it will only radiate its heat away. So it will remain in molten state for very, very, very long time. You did that on Earth, it will cool down much quicker. Why? Because even though the temperature is higher, there is a lot of convection. Convection trumps radiation emission by hundreds of times, hundreds to thousands of times. Now on top of that, it has an atmosphere, so again it has a lot of convection. Then it has a much higher density of atmosphere, because like almost 1.5 times. So it will take a lot more molecules. A lot more molecules will hit the hot object and extract the energy out of it, so it will cool down faster. On top of that, anytime you are dumping something, like let's say you have molten lead, if the amount of heat dumped will go somewhere. It is very large. That's the whole point. This is why it is cold. Like moon and all that, it's quote unquote cold. This is actually cold. So basically, if you built an insulator suit that is more than good enough to handle vacuum of space, it will perfectly work on Mars. It will perfectly work on basically moon and all that. You don't have to worry about it. The moment you took that suit in basically here, you did. Because the suit will, like, it's one thing to design something to withstand radiation exposure, basically to make sure that infrared radiation goes back. Here you have to design something that is very thick, like I mean like upwards of like a half inch, basically half foot thick. You have to make sure, so otherwise you will not freeze to death, because you have to know convection is much more powerful than that, and it has wind. So it's not even like, okay, there is atmospheric pressure, there is wind, like there is circulation. So you have to understand, this is the coldest usable place we have. Then it has a lot of nitrogen. How much nitrogen? Now again, I can give you a very large number from Wikipedia. That does not mean anything. Think of it this way: it has more nitrogen than the Earth. Then we come to the liquid part. It is the only known place where we actually observe proper liquid and with flow. So what do I mean by liquid and flow and all that? Basically there rains. It rains there. It has tornado, it has cyclones, it has lakes, it has pond, it has sea, everything like Earth. Only difference is Earth has water, this got basically hydrocarbon. From methane to anything, ethane and propane can also be found. So you have to understand that. So methane is the primary liquid component here, and nitrogen is the primary atmosphere. It is cold. It is ludicrously cold. So and people are still expecting that there is a subsurface ocean here also. Again, there is a very serious risk that it might be just methane. That's Titan. Now we come to Europa. This is the favorite moon of Neil deGrasse Tyson, and there is a very good reason for that. You have to understand, this is the smallest of the 4 Galilean moons. Now, what does this Galilean moon, we have to say? To give you a simpler context, think of this, there are hundreds of moons. So how do we classify it? We classify it based on the gravity and the way we discovered it. Now these moons are so big that Galileo discovered with a tiny telescope. Now other things, we had to send satellite there. We have to send probes there to detect them. They are that small. Like even with our modern telescope, we can't detect most of them. So there is a classification. You have serious moon, quote unquote Galilean moons, and then there are puny moons. To give you a mathematical context of this, Ganymede, the biggest one, is 37.69% of the total lunar mass. Basically, every moon combined, you will get 37% just from Ganymede. And then you come to Callisto, that is 23%. Then you come to Io, only volcanically active place we know other than our own solar system, which is upwards of 22% of the mass. Then we come to Europa, which is 12%. Here's the deal, everything else, aka more than hundreds of the moon combined, would barely make 0.0003%. So that's why people classify moons as two independent categories. Category number 1, Galilean moons. Category number 2, garbage. So the interest in this is very critical because this surface is active. Basically, lunar surface is not that active. It's like only gets destroyed when either moon is cooling down right now, so it's shrinking slowly, but it's not that fast. You cannot be like, oh, I observed today something this and I observed tomorrow something that. No, but Europa is very active. Reason for that is because the way its orbit is around its basically gas giant, is that it's getting tidal forces, so it's getting like squished. Basically, it's getting a serious amount of thermal heating from the inside. Basically, that's why it's heating from the inside. Now, the outside shell, the crust, if you will, is basically ice. Now, here's the funny thing about ice. Ice is a very good insulator. So, if you have heat trapped inside, it will make a liquid ocean. Now, again, at this point in time, we are 99% sure that there is a liquid ocean, but we cannot justify it unless we can actually go there. We cannot be like, yeah, there is. Right now, it's like almost 99% sure. So, but we do not know the condition there. Now, it could be liquid by other reason also. Like, let's say you take a liquid and you start to cool it out, but you compress it to a point where it cannot like freeze. It simply won't freeze. Basically, you're using pressure to keep it in a liquid state. Something similar that could have happened here also. But at this point in time, we are like almost certain that it has a liquid ocean, and it's the core heater of it is basically from the gas giant, and the reason why it's not freezing even though it's that cold out there is simply because it's insulated by the giant ice layer. So, but here's the funny thing, this is why I hate Elon Musk, is simply because he gets very emotional, and on one of his presentation he had somebody land here, basically like BFR, or early days of BFR presentation. Here's the deal, this is inside Valerian radiation belt of Jupiter. You're gonna basically roast yourself to death by radiation if you even try to go there. Like, the only way to go there, you have to go like at like orbital speed very quickly, and you have to go as quickly as possible as inside the ice sheet to make sure you are not radiated. This is the very critical aspect. These places are not suitable for human living, but they are good enough for robotics. So you have to understand that subsea ocean is the very interesting part, and the fact that it is one of the smallest, and like this is like manageable scenarios. Other places are like Io. Even though Io is bigger, it's flat out radioactive and flat out volcanic, so we really can't do anything there. But Europa is very interesting to us. So why bother with these things? A, these things are very far. B, these things are really far, as in it takes 10 years to go there. So why the heck we even want to bother with that? Now you have to understand that when sun is formed, it creates a shock wave. When star is ignited, not like formation of star is different than ignition of a star. Formation is basically gravity starts to clump together. All the things will come together in one central place. But when you have ignition, basically when it goes kaboom, it creates a shock wave. Now that shock wave pushes out every lighter element. So heavy elements always get deposited in the basically inner ring, and the outer ring ends up getting light elements. That's why hydrogen and nitrogen, if you want to find light elements, you have to go far. Now if you want something like heavy, iron and all that, you will find them in like Mercury, Mars and all that. So if you want light element, specifically hydrogen, this is the best place to find it. Now again, moon are relatively, even the biggest moon, even Titan, relatively speaking, is much easier to get in and get out than Mars. So this is very interesting part, and Titan is actually uniquely beneficial because you can use parachute to land there. So that's helpful. And in terms of getting out, you can use basically space elevator, because it's not, the gravity is not strong enough that you need magic material. You can make it out of Kevlar also. So getting in and out is quote unquote easy, relatively speaking. Now it's also very easy to extract this thing. Now the reason why I have quote unquote for easy is basically you have liquid basically methane. This is a very good source of hydrogen. You're like, why the heck you want to do this rather than like, you know, melting the ice, then converting that ice into liquid form, then electrolysis. Think of it this way: the bounding strength of carbon plus hydrogen versus carbon plus I'm saying hydrogen plus oxygen is completely different. Basically, if you want to do electrolysis, you have to spend a lot of energy. If somebody gives you hydrocarbon and says remove hydrogen from it, we call it steam reforming. It's much easier, and that's how all the rocket fuel that you see right now in use in Earth generally comes from that, because liquid hydrogen is much easier to extract. not liquid hydrogen. Hydrogen is much easier to extract from hydrocarbon. So having a liquid form of hydrocarbon there, and which is methane, which is really easy to basically steam form, we can really utilize this. This is very awesome. And it also has a nitrogen, which is very critical. If you really want to terraform, let's say Venus or let's say Mars, you need a lot of nitrogen, and that amount of nitrogen you cannot ship from Earth. So you have to go here. Now, only side effect is that it does suffer one serious consequences, that solar panels are flat out useless. RTGs will work amazingly well here, simply because RTGs require what we classify as temperature delta. Basically, you want to have hot side and cold side. In the vacuum, quote unquote, it's cold, but it's not cold enough because you don't have convection. Here, RTG that is like, let's say, rated for 500 watt will give you kilowatts of power here very easily, because convection will pull heat away very quickly. So again, you can utilize RTGs, and you have to use a nuclear reactor like NASA's kilowatt nuclear reactor. That will work amazingly well here. So these places are rich enough that if you want to build a planet, let's say you want to terraform Venus and terraform Mars, these places have more than enough. They're like, I got you. Basically, you don't have to strip Earth to make another Earth. These places have more than enough. So this is why we want to take other moons seriously. Now there is another aspect that we can do. Basically, we form a grid. Now this grid, I'm talking about astrophysics grid, basically lots of outposts, lot of listening station, lot of radio to astronomy. The reason for that, it will allow for better protection. So you have to understand, there is something known as asteroid belt. Now most of the asteroid belt is outside of Mars and inside of Jupiter's orbit. Now if you can observe from Earth, we already are observing it, but we only get a small portion. But if you observe from Jupiter, you get much larger field of view. So, and in terms of tracking orbits, here's a simple answer: more is better. Now if you have something that far, you you can see much fainter objects, and you can get much more accurate prediction. Because you have to understand, the movie made us like dumb and showed us the fact that you can have large objects that can kill a planet. We're gonna miss that. No, we're not gonna miss. Large objects are very easy to spot. It's basically like somebody telling you, hey, spot basically truck 100 kilometers away. You can easily spot it, because if it's in a desert, you can spot it. Even if it's in like crowded environment, you can still guess it. But if somebody says, hey, spot like let's say hair clip, you can't do that. You can't do, like, if I put this like 10 meters away, you will have a hard time finding it. If I put it 100 meters away, good luck finding it. And if I put it 100 kilometers away, or basically 10,000 kilometers away, you're not gonna find it. Now these basically hair clips, they are city killers. That's the problem with that. So right now our Earth space defense grid is more than good enough to defend the planet, but it's not good enough to defend the city. So basically that incident that happened in Russia, where a small asteroid that almost destroyed a city, like that would have made such a big impact that if it would have touched the surface, the maps would have been redrawn. Basically the map would be like, there used to be something here, there would be a big circle there, basically a big crater. So that impact was, we are lucky that it came, like unlucky because it came from the sun side, that's why we did not spot it. Lucky because it entered at a very shallow angle. It's like almost a skip stone, but due to its velocity, it did not skip outwards, but it did enter, but it crashed directly, and the angles were so shallow that it did not touch the surface. If it would have touched the surface, that place would have been evaporated. It's like there used to be something here. It won't be like Hiroshima or Nagasaki, like there used to be something here. It's like gone. So using this, basically using the fact that distance from Jupiter and Saturn and all that, we can really get a much more precise measurement and defense grid. And also good for astronomy, basically astronomy. Basically, the more instruments you have, the more places you have the instrument, because many things you require what we classify as radial velocity measurement. Some places require it as like parallax movement. Basically, you take left eye, right eye, left eye, right eye. Now, the way we do it on Earth is basically we wait from basically 6 months apart. That's how you get from Earth, you can measure the distance. Doing this on Jupiter, it will allow us much higher, much more precision astrophysics. This is really useful. Like, you really want to see, first, for safety reason, you want to find out small objects that are like city killers, and in terms of astrophysics, the contribution would be amazing. So this was my presentation on other moons of our solar system. I hope you liked it, learned from it. In that case, please leave a like and click the basically older videos of mine. And if you didn't like it, don't worry about it. You can press dislike. I would urge you to press it twice to show me your extra disappointment, and leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.